Welcome back to the deep dive. Today, we're setting our sights on a truly fascinating region of our solar system. It's often dismissed, as just a collection of cosmic rubble.
Yeah, rocks floating around.
Exactly. But it actually holds these incredible stories about our planetary origins, surprising threats, and maybe even untold riches that could, redefine humanity's future. We're talking, of course, about the asteroid belt.
It's that dusty ring between Mars and Jupiter.
That's the one. And for this deep dive, you've asked us to unravel some pretty big cosmic mysteries. Why is it even there? Did a planet not form from it? And, if so, why? What was Jupiter's role in all this?
Ah, the big guy.
Yeah,
Always involved.
always. And are we safe from its inhabitants? Or are we kind of living in a cosmic shooting gallery? Do other star systems have their own versions? And maybe the most exciting bit, are there really valuable resources hidden in those rocks, just waiting?
The trillion-dollar question, maybe literally.
Maybe. So our mission today is to sift through the latest science, the newest discoveries, and pull out the most important nuggets of knowledge. We really want you to walk away from this conversation feeling not just informed, but genuinely kind of shifted in your understanding of this seemingly empty region.
Yeah, there's more to it than meets the eye.
Definitely. Get ready, because your perceptions of the asteroid belt are probably about to be utterly reshaped. The asteroid belt, our solar system's cosmic construction site. Okay, let's unpack this. When most of us picture the asteroid belt, we're probably, thinking of those scenes from Star Wars or something.
Right, dense, chaotic, impossible to fly through.
Exactly, a minefield of tumbling rocks, constant dodging. It's dramatic, but the reality is actually quite different and maybe far more interesting than the Hollywood version.
Much more subtle, yeah.
So imagine this vast sort of donut-shaped region, a torus, nestled right between the orbits of Mars and Jupiter. That's our main asteroid belt.
The primary collection, yeah.
But here's the kicker. It is, in fact, mostly empty space. Seriously.
It really is surprisingly sparse.
The individual asteroids are spread out over such an immense volume that, on average, they're about 1,000,000 kilometers apart. That's, 600,000 miles?
Roughly, yeah. It's vast.
It's like putting a few pebbles in an entire ocean. And this incredibly low density is exactly why so many spacecraft, Pioneer 10, 11, the Voyagers, Ulysses, Cassini, Juno, they've all just sailed right through.
Without any issue, pretty much.
The odds of a random collision for a probe are estimated at less than 1 in a billion. So, yeah, not the cosmic dodgems we imagine.
No, thankfully not. But what's fascinating, despite that emptiness, is that it is still considered the smallest and innermost circumstellar disk in our solar system.
Circumstellar disk.
Oh.
So like material orbiting the star.
Exactly. Think of it like Saturn's rings, but way, way bigger and much, much more spread out. And our main belt is distinct. It's separate from other groups, like near-Earth objects.
Ones that get close to us.
Right. And the Kuiper belt objects way out past Neptune, or the really distant Oort cloud stuff. This distinction, it tells us a lot about how it formed and evolved differently. It's a key piece of the solar system puzzle.
Okay, so it's sparse, but it's a defined region.
Definitely. And while we talk about millions of asteroids, if you could somehow squish them all together,
Yeah.
their total combined mass would only be about 3% of our moon.
3%, that's tiny.
It's surprisingly small, considering the space they fill. And most of these main belt asteroids, they follow these slightly elliptical, pretty stable orbits. They all go around the sun the same way Earth does. Takes them maybe 3 to 6 years for one lap. So they're spread out, but they're not just random. They're gravitationally part of the system, moving in a relatively orderly dance.
Okay, so not the chaotic rock field, but still significant, just sparse. And you mentioned within this sparse neighborhood, there are some real giants holding most of that tiny mass. That sounds like there's more structure to it.
Exactly. You've hit on a key point. A big chunk, maybe 60%, of the belt's total mass is locked up in just 4 objects. Ceres, Vesta, Pallas, and Hygiea.
The big 4.
The titans of the belt, yeah.
Yep.
Ceres is the biggest, about 950 kilometers across. It's actually classified as a dwarf planet.
A dwarf planet, like Pluto, but in the asteroid belt.
Exactly like Pluto in terms of classification. It's massive enough that its own gravity has pulled it into a nearly perfect sphere. Unlike the lumpy potato shapes we usually think of for asteroids.
Wow.
Then you have Vesta, Pallas, and Hygiea. They're smaller, less than 600 kilometers across. And then everything else ranges right down to, dust and pebbles, basically, meters across. So it's a hierarchy, a few big players, and countless smaller bits.
Right, which brings us right to that huge question. Why isn't there a planet there? It just feels like there should be one. You mentioned that Tish's-Bode law, that pattern. It practically pointed a finger right at that spot.
It did. And that raises a really fundamental question about how solar systems form. And the answer is all tangled up with Jupiter.
Ah, Jupiter again.
Always Jupiter. You're right about the Tish's-Bode law.
Yeah.
This interesting mathematical pattern predicted a planet around 2.8 astronomical units out from the sun,
Which is right in the belt.
smack dab in the middle.
Uh-huh.
So when Giuseppe Piazzi found Ceres there in 1801, right at that distance, he initially thought, Eureka, I found the missing planet. There was even this group, the Celestial Police,
Yeah.
hunting for it.
Yeah.
But the real story is more complex. It's about how planets form.
Okay.
The asteroid belt started out as planetesimals, these kilometer-sized building blocks in the primordial solar nebula, that big cloud of gas and dust. They're starting to clump together, accreting.
Trying to build a planet.
Exactly. But before they could really get going, Jupiter, our solar system's giant, became the dominant gravitational force nearby. And its gravity just disrupted everything.
Disrupted how? Like just pulled them away?
More like stirred them up violently.
Yeah.
Imagine trying to build a sandcastle while someone keeps kicking sand at it. Jupiter's immense gravity kept giving these forming bodies, these planetesimals, and even early protoplanets.
Bodhi planets.
Yeah, things maybe hundreds of kilometers across already. It kept giving them these huge gravitational kicks. It pumped so much extra kinetic energy, so much speed into their orbits.
So they were moving too fast?
Way too fast. So instead of gently merging when they collided, they smashed into each other violently. They shattered.
Oh, wow. So collisions became destructive instead of constructive.
Precisely. Jupiter basically turned the region into a demolition derby. And this process was incredibly efficient. It caused a loss of something like 99.9% of the asteroid belt's original mass.
99.9%.
Gone. Blown out of the region, mostly within the first 100 million years or so of the solar system's history. It was a massive clearing out.
So Jupiter acted like a cosmic bouncer, basically. Threw almost everyone out and stopped a planet from forming. Incredible. And its influence. It's still felt today, right? It didn't just start back then.
Not at all. Its influence continues to sculpt the belt. Whenever an asteroid's orbital period, the time it takes to go around the sun, forms a simple mathematical ratio with Jupiter's orbital period. That's called an orbital resonance.
Like pushing a swing at the right time.
Exactly like that. Jupiter's gravity gives these asteroids in resonance a consistent nudge over and over, amplifying the effect. And these nudges tend to destabilize their orbits, eventually kicking them out of that resonant path.
And that creates gaps.
That creates the Kirkwood gaps. These are distinct regions within the belt where there are noticeably fewer asteroids. They line up perfectly with these strong Jupiter resonances. It's clear evidence of Jupiter's ongoing gravitational meddling.
Fascinating. So it's still actively shaping things. Now, I've also heard about something called the grand tack hypothesis. Does that add another layer to Jupiter's role? Maybe suggest it wasn't always where it is now?
Oh, it absolutely does. The grand tack adds a really dramatic chapter to Jupiter's story. It proposes that Jupiter didn't just form and sit there. Early on, it actually migrated inward, maybe as close to the sun as Mars is now.
Whoa, really? That close?
Yeah, potentially. And then, due to interactions with Saturn, it tacked, like a sailboat changing direction, and migrated back outward towards its current position.
A cosmic road trip.
Pretty much. And this inward and outward journey would have had a profound impact. As Jupiter moved inward, it would have scattered rocky planetesimals from the inner solar system outwards.
Towards the asteroid belt region and beyond.
Exactly. And as it moved back out, it likely dragged icy bodies from the outer solar system inwards, seeding the asteroid belt region with them.
So it basically stirred the pot on a massive scale.
A huge scale. It helps explain the mix of asteroid types we see today, why we have both rocky inner system type asteroids and more icy outer system type asteroids coexisting in the belt. It made the whole region much more diverse than it might have been otherwise.
That's a phenomenal picture. Jupiter as this giant migrating sculptor. So, given this history, the destruction, the scattering, the mixing, what are these leftover bits, this 0.1%, actually made of?
Right, let's look inside them. We classify asteroids mainly by looking at the light they reflect, their spectra. It's like a chemical fingerprint.
Okay.
And broadly, they fall into three main groups. First, the C-types for carbonaceous. These are dark, rich in carbon, maybe water too. They make up about 75% of known asteroids.
The majority, then.
By far. They're more common in the outer parts of the belt, where it was colder. Then you have the S-types for silicaceous. Stony asteroids rich in silicate rock, like Earth's mantle. They're about 17%. more common in the inner belt.
Okay, C-type's dark and outer, S-type stony and inner. What's the third?
The M-types, for metallic. These are metal-rich, lots of iron and nickel. They're rarer, but really interesting. They might be the exposed cores of those protoplanets that got smashed up early on.
The literal heart of a baby planet.
Potentially, yeah. And within these broad types, the diversity is amazing. Take Ceres, the dwarf planet.
Yeah.
It seems to have a rocky core, but it's covered by an icy mantle. Suggests it might have formed further out, past the snow line where ice could easily form, and then got pulled in.
Maybe during that grand tack.
Possibly. Whereas Vesta, another big one,
Ups.
it's different. The Dawn mission showed it likely has a nickel-iron core, an olivine mantle, and a basaltic crust. It's differentiated, like a tiny terrestrial planet.
Wow, layers, just like Earth.
Exactly, right there in the asteroid belt.
It really shows they're not just uniform rocks. Now, I heard something recently about Hygiea, another one of the big four, something about its shape.
Yes, Hygiea. That's a fantastic recent story.
Ah.
Using the Very Large Telescope, astronomers got incredibly detailed images. And they found Hygiea is almost perfectly spherical.
Spherical, so like Ceres, another dwarf planet candidate.
Potentially. It might just squeak into the dwarf planet definition, becoming the smallest one known, just over 430 kilometers across. But what was really surprising was why it's spherical. People expected to see a giant impact crater, because there's a whole family of smaller asteroids that clearly came from Hygiea after a massive collision. Yeah. But the crater isn't there.
Huh. So where did the family come from?
The simulation suggests something incredible. About 2 billion years ago, a huge impact doesn't just crater Hygiea, it pulverized a big chunk of it. The main body was basically turned into molten debris.
Oh my God.
And then gravity pulled that hot, molten mess back together, and it cooled and hardened into the nearly perfect sphere we see today.
It reformed itself after being shattered.
Essentially, yes. A self-healing or self-reforming planetary body. It's amazing.
That is absolutely mind-blowing. Are there other discoveries blurring these lines, like finding water where we didn't expect it?
Definitely. On Ceres, back in 2014, the Herschel Space Observatory definitively detected water vapor erupting from its surface. Plumes, like you see from comets.
Water vapor from an asteroid.
Well, a dwarf planet in the asteroid belt. It really blurred the lines. And then, even more intriguingly, we found these main belt comets.
Comets in the main asteroid belt. I thought comets came from way out.
Traditionally, yes. But these are objects with asteroid-like orbits, firmly within the main belt, but they sometimes show cometary activity tails, commas probably when small impacts expose subsurface ice, which then sublimates in the sunlight.
Wow, so icy asteroids.
Pretty much. And here's the kicker. These main belt comets might have been a major source of Earth's oceans.
Really? How?
Their water has a deuterium to hydrogen ratio that's like a chemical fingerprint for water origin that matches Earth's ocean water much better than the water from classical outer system comets.
So the water we drink might have come from the asteroid belt.
It's a very strong possibility. It connects the belt directly to the habitability of Earth. And it gets even better. In 2019, scientists found sugars, including ribose.
Ribose, like in RNA.
Exactly. A fundamental building block for life. Found in meteorites that came from asteroids. It suggests complex organic chemistry, maybe even prebiotic chemistry, is happening on these bodies. It fuels ideas about the RNA world or even panspermia life's ingredients traveling through space.
The asteroid belt as a source of water and life's building blocks. That completely changes the picture from just dangerous rocks beyond our belt. Asteroids, threats, and resources. Okay, so we've redefined the belt dynamic, diverse, maybe even life-giving, but let's face the pointy end of the stick. While the main belt itself is sparse, what about the objects that do get knocked out, the ones that come near Earth? Are we actually safe? That impact threat still looms large.
Right, and that's where the focus shifts from the main belt itself to the near-Earth asteroids, or NEAs. These are the ones whose orbits bring them into Earth's neighborhood.
And many come from the main belt.
A lot of them do, yeah. Kicked out by those same gravitational nudges from Jupiter we talked about, or sometimes there may be old, dead comets that have lost all their ice and just look like rocky asteroids now.
Okay. And how many are we talking about?
Oh, as of early 2022, we'd identified nearly 29,000 NEAs. And crucially, about 878 of those are a kilometer or bigger in diameter.
A kilometer. Why is that size significant?
Because that's generally considered the threshold for potential global catastrophe. An impact from something that big could throw so much dust and debris into the atmosphere that it dims the sun for months, maybe years.
Causing, like, an impact winter, global crop failures.
Exactly. It's a civilization-level threat. We're not talking dinosaurs necessarily, but it would be devastating on a planetary scale.
That is terrifying. And we've seen smaller, but still scary reminders, right? Like Chelyabinsk.
Chelyabinsk in 2013 was a major wake-up call. That was maybe a 20-meter object about the size of a 6-story building. It didn't hit the ground intact. It exploded in the atmosphere.
But the shock wave...
The shock wave was immense.
Yeah.
The energy released was like 500 kilotons of TNT, maybe 30 times that Hiroshima bomb. It blew out windows over a huge area, injured about 1,500 people, mostly from flying glass. It showed vividly what even a relatively small airburst can do.
And we didn't see that one coming, did we?
No, it came in from the direction of the sun, making it very hard to detect with ground-based telescopes beforehand, which highlights the need for constant vigilance and diverse detection methods.
Okay, so the threat is real, but we are looking, right? What's being done?
Oh, yes. Thankfully, there's been a huge international effort. NASA's Space Guard survey, started back in '98, aimed to find 90% of the NEAs larger than 1 kilometer.
And did they succeed?
They did. By 2012, they'd met that goal, which is fantastic news. And the really crucial part, none of the large ones found so far are on a collision course with Earth anytime soon.
That's a huge relief.
It is. And the search continues for smaller ones, and we have ongoing monitoring. Like, remember Asteroid 2024 YR4? Initially, there was a small but non-zero chance of impact in 2032.
Vaguely.
Further observations very quickly ruled that out. Our ability to track and refine orbits is getting much better. So yes, the threat is real, but we are actively watching the skies. Our planetary defense playbook, how we could act.
Okay, so we're watching, but let's play this out. What if we do find one, a big one, or even a Chelyabinsk-sized one heading our way with our name on it? What can we actually do? What are the options on the table?
Right. This is planetary defense in action. And the strategies basically fall into 2 main camps. First, there's fragmentation.
Blowing it up, like in the movies.
Sort of, yeah.
Yeah.
The idea is to break the impactor into lots of smaller pieces and scatter them so they either miss Earth or are small enough to burn up harmlessly in the atmosphere.
Is that feasible? Especially for big ones?
It's tricky. For very large asteroids, especially if we have very little warning time, like less than a year, some studies suggest a nuclear explosion might be the only thing powerful enough.
Nuclear weapons in space. That sounds intense.
It is, and obviously carries huge risks and political implications.
Yeah.
But concepts like the HAIV Hypervelocity Asteroid Intercept Vehicle propose using a kinetic impactor first to make a crater, then detonating a nuclear device inside that crater to maximize the push. It's seen as a potential last resort for the biggest threats.
Okay, fragmentation as a last resort. What's the other option?
The second generally preferred approach is delay or deflection. This uses orbital mechanics to our advantage.
How so?
An impact only happens if Earth and the asteroid arrive at the same point in space at the same time. Earth is about 12,750 kilometers wide, and it's moving at 30 kilometers per second. So it crosses its own diameter at about 7 minutes.
Okay.
So if you can just change the asteroid's arrival time at that intersection point by a little more than 7 minutes, either speed it up or slow it down, it will miss Earth entirely.
Just nudge it enough so it arrives too early or too late.
Exactly. It doesn't necessarily take a huge push, especially if you do it far in advance. Years or decades of warning time allow even a tiny nudge to add up to a significant miss distance.
That sounds much more elegant. And we've actually tested that, right? The DART mission.
Yes. DART was a spectacular success and a huge milestone for planetary defense. That was the kinetic impactor method.
Crashing something into the asteroid.
Right. NASA crashed the DART spacecraft into Dimorphos, the small moonlet orbiting the larger asteroid Didymos. And it worked even better than expected.
How much did it change the orbit?
It shortened Dimorphos's orbital period around Didymos by 33 minutes. The goal was just over a minute. It proved that we can physically move an asteroid in a predictable way. Data suggests this method could work for asteroids up to maybe half a mile across, given enough lead time.
That's fantastic. Proof of concept. Are there other deflection ideas being explored?
Oh, loads. Some are more futuristic, but grounded in physics. Things like mass drivers putting automated systems on the asteroid to throw rocks off it, creating a slow, steady push.
Using the asteroid's own material as propellant.
Exactly. Or attaching direct force rocket engines like highly efficient ion thrusters to just continuously push it.
Like strapping a motor to it?
Pretty much.
Yeah.
Then there's asteroid laser ablation, using powerful lasers to vaporize surface material, creating tiny jets that push the asteroid. Or huge solar sails to use the pressure of sunlight.
Sunlight pressure. That works.
It's tiny, but over years or decades it adds up, especially on smaller asteroids. Or even painting the asteroid, making it white to reflect more sunlight. Or black to absorb more heat and use the Yarkovsky effect, which is a subtle thermal thrust.
Wow. Some really clever, subtle ideas there, too.
Absolutely. There's also talk of using steam clouds to create drag, or even magnetic flux compression for metallic asteroids, using electromagnets to slow or grab them. Lots of ingenuity being applied.
It really sounds like we have a growing toolbox, but I remember Carl Sagan raising a really important, almost chilling ethical point about this kind of technology.
He did, and it's profoundly important. Sagan worried that any technology powerful enough to deflect an asteroid away from Earth could also potentially be misused to deflect a harmless asteroid towards Earth.
Weaponizing asteroids.
The ultimate high ground, in a terrifying way. He argued that humanity might be at greater risk from a deliberately caused impact than a natural one if we develop this capability without strict international control and oversight.
A sobering thought. So international cooperation is key.
Absolutely critical. Groups like the International Asteroid Warning Network, IAWN, for detection, and the Space Mission Planning Advisory Group, SMPAG, for coordinating response strategies are vital for building trust and ensuring these tools are used only for planetary defense for the benefit of all humanity. It's a huge responsibility. Cosmic treasure chests, the allure of asteroid mining.
Okay, so we're learning how to defend ourselves. But maybe these asteroids aren't just threats. Let's pivot from prevention to profit. We hear whispers of space gold rushes, immense wealth floating out there. Is there really treasure in them, our hills? Or rocks?
Huh. Well, the potential is definitely immense. Asteroids really are cosmic treasure chests, although, getting to them and opening them is the hard part. Researchers are mainly looking at three types of resources.
Okay, what are they?
First, free metals. This includes the really valuable stuff, especially platinum group metals, platinum, palladium, rhodium, iridium. These are much rarer on Earth's surface because they mostly sunk to the core when the planet formed.
But they stayed mixed in asteroids.
Exactly. They didn't undergo that same large-scale differentiation. Second, volatiles. Mostly water ice, but also maybe ammonia, methane, other organic compounds.
Water we already talked about being super valuable in space.
Hugely valuable. For fuel, for life support. And third, just bulk dirt. Asteroid regolith. Sounds boring, but it could be great for radiation shielding or construction material in space. Cheaper than hauling it all up from Earth.
Let's go back to those metals. Platinum, palladium, rhodium. They're expensive here. What kind of prices make asteroid mining seem worthwhile?
Well, the prices fluctuate, but you're talking hundreds, even thousands of dollars per ounce. Platinum, maybe $830, palladium, $960, rhodium, over $2,200, iridium, $1,400 an ounce. Even gold, around $1,200 an ounce, is like $39 million per metric ton.
Wow. So even a smallish metal-rich asteroid
Could represent literally trillions of dollars in potential value. It's an almost unbelievable concentration compared to terrestrial ores.
And are there specific asteroids known to be rich in metals?
The M-types are the prime candidates, and the most famous one is 16 Psyche. It's thought to be the exposed nickel-iron core of a protoplanet that got stripped of its crust.
The heart of a planet again.
Exactly. It's this giant ball of metal. NASA's Psyche mission, launched in October 2023, is on its way right now to study it up close. It'll tell us a lot about planetary cores and potentially about the feasibility of mining such an object.
Fascinating. And water, you keep saying, is maybe even more valuable in space.
In the context of enabling large-scale space operations, absolutely. You can split water, H2O, into hydrogen and oxygen. That's prime rocket fuel.
Right.
It's also breathable air for astronauts. And bulk water ice is surprisingly good radiation shielding. If you can source water from asteroids, especially icy ones like Ceres or those main belt comets.
You don't have to launch it all from Earth.
Exactly. Launch costs are a killer. If you can refuel spacecraft in space using asteroid water, suddenly missions to Mars, the outer planets, even establishing bases become dramatically cheaper and more feasible. It could unlock the solar system, the economics and logistics, making space mining a reality.
Okay. The resources are there. The value is potentially astronomical. But actually doing it mining in space sounds mind-bogglingly complex and expensive. What are the biggest hurdles beyond just getting a spacecraft there?
Oh, the hurdles are immense. It's not just the tech. The economics and logistics are maybe even tougher right now. We saw early private companies like Planetary Resources and Deep Space Industries.
Yeah, I remember them. Big hype.
Huge hype.
Uh,
But they ultimately folded. The development costs were just too high, and the return on investment was too far in the future for most private investors. It requires incredibly patient capital.
so funding is a major issue.
Huge. And there's also the weird economic question.
Yeah.
If you did manage to bring back, say, tons and tons of platinum, would you crash the market price on Earth?
Right, making it less valuable.
Possibly. Or maybe cheaper platinum would suddenly create all sorts of new industrial demands we haven't even thought of. It's hard to predict.
And the actual mining process in space.
Yeah, the infrastructure needed is staggering. You need power, lots of it reliably. You need ways to contain and handle materials in zero-G or microgravity. You need refining processes that work without gravity. You need robotics, maintenance, all in the harsh environment of space, millions of miles from the nearest hardware store.
It's a monumental engineering challenge.
Monumental. Rethinking entire industrial processes for space.
So, given these huge challenges, what's the path forward? How does this actually become viable?
Well, several strategies are emerging. One is government support. Governments see the long-term strategic value, so places like the U.S. and Luxembourg are putting funding into research and development, creating legal frameworks, trying to kickstart the industry where private money might hesitate.
Providing that patient capital.
Exactly.
Uh.
Another huge area is in situ resource utilization, or ISRU.
Using resources in space for space.
Precisely. The first best customer for asteroid resources might be other space missions. Mining water ice to make rocket fuel for a Mars mission is probably much more economically viable in the near term than bringing platinum back to Earth. It lowers the cost of everything else we want to do in space.
Makes sense. Build the infrastructure using local materials.
Right. And then there's targeting the low-hanging fruit, these easily recoverable objects, or EOs, small near-Earth asteroids that don't take much energy to nudge into an orbit near Earth where we could more easily access them.
Bring the mountain to Muhammad, sort of.
Kind of. There are already a dozen or so identified that might be reachable with current tech. And then, of course, advanced technologies, robotic mining systems, maybe drone tugboats to slowly haul asteroids, maybe refining materials on the moon first. Automation is key.
It's a long game. What about the legal side? Who owns this stuff? Can a company just go mine an asteroid?
Ah, the legal frontier. The main treaty is the Outer Space Treaty of 1967. It says space is for all mankind, and no nation can claim sovereignty over celestial bodies.
So no planting flags and saying, this asteroid is mine.
Right. But the interpretation generally is that while you can't own the asteroid, you can extract and own the resources you get from it. Like fishing rights in international waters. You don't own the ocean, but you own the fish you catch.
Okay, that's the general idea.
But it's still debated internationally. The U.S. passed the Space Act in 2015, explicitly giving U.S. citizens rights to own and sell space resources they recover. A 2020 executive order doubled down, saying the U.S. doesn't see space as a global commons and supports commercial extraction.
So the U.S. is pushing for a finders keepers approach.
Pretty much to encourage investment. But not all countries agree with that interpretation, so it's still a legally gray area internationally.
And environmentally. Mining on Earth is often destructive. Is space mining cleaner, or does it just create new problems?
That's the double-edged sword. On one hand, mining asteroids for metals could take huge pressure off Earth's ecosystems. Less terrestrial mining means less habitat destruction, less pollution here. That's a major potential benefit.
Moving heavy industry off planet.
Exactly. But on the other hand, we have to be careful not to just trash the space environment. Mining operations could create clouds of debris, potentially harmful dust, or alter asteroid surfaces in unpredictable ways. We need careful planning and regulation to avoid creating a new tragedy of the commons in space. Beyond our solar system, our asteroid belt's common.
What an incredible range of issues, from planetary defense to cosmic economics and ethics. Let's zoom out one last time. Our asteroid belt, shaped by Jupiter. Is it just a fluke of our system, or do we see things like this around other stars?
This is where things get really exciting for understanding our place in the cosmos. The answer is, our asteroid belt is definitely not unique. Observations, especially with infrared telescopes, show that debris disks are actually quite common around other stars.
Debris disks. So, belts of dust and rock, exoplanetary asteroid belts.
Exactly. They're the equivalent of our asteroid and Kuiper belts around other stars. Finding them tells us that the processes that formed our belt's planet formation, gravitational scattering by giant planets, these are likely universal processes.
So where you find planets forming, you probably find leftover debris being sculpted into belts.
That seems to be the case. And just like Jupiter shapes our belt, the structures we see in these distant debris disks can actually hint at the presence of unseen planets in those systems. Webb's groundbreaking discoveries.
And the James Webb Space Telescope has given us some amazing views of these, right?
Oh, absolutely groundbreaking views. Webb looked at the Fomalhaut system about 25 light years away. We knew it had a debris disk, but Webb's detail was stunning.
What did it show?
Not just one ring, but complex nested rings of dust. Webb revealed two distinct inner belts like asteroid belts, plus the big outer Kuiper belt-like ring, and maybe even a huge dust cloud from a recent collision. It's a much more intricate system than we realized.
Two asteroid belts. Wow. What does that tell us?
It's incredibly suggestive. Anytime astronomers see gaps and sharp edges in rings like that, it screams planets. Unseen planets embedded within the disk, gravitationally sculpting those structures, clearing gaps, shepherding the dust.
Just like Jupiter and the Kirkwood gaps here.
Precisely. It strengthens the case that there are probably multiple planets orbiting Fomalhaut, carving out that complex architecture. Finding those planets directly is the next step, but the debris disk is like a giant signpost pointing towards them.
So these belts are clues to hidden worlds.
They really are. And Fomalhaut isn't the only one. Epsilon Eridani, another nearby star similar to the Sun, also shows evidence of a complex debris disk with gaps suggesting planets. It reinforces the idea that this interplay between planets and leftover debris is just how solar systems normally evolve. Our system isn't weird. It's likely a common outcome. Outro.
What an incredible journey we've taken through the asteroid belt from, its origins as this sort of failed planet,
Yeah.
utterly shaped by Jupiter,
Yeah, Jupiter's a sculptor.
to its potential as the source of maybe invaluable resources, driving our future in space, and even its role as this key clue pointing to how planets form everywhere.
It connects our past, present, and future, really.
It really does. We've explored how surprisingly empty it is, debunking the movie myths, but also the very real threat from those objects that do get knocked towards us.
And the amazing ingenuity going into planetary defense.
Exactly. And peering out with tools like Webb to see these cosmic construction sites are, well, seemingly everywhere, a universal feature.
Yeah, it seems planet formation leaves behind these telltale rings.
So this deep dive really shows the asteroid belt is so much more than just a dusty ring. It's dynamic, it's informative, potentially vital, a huge part of our cosmic story.
Absolutely. A crucial piece of the puzzle.
So as you look up at the night sky, maybe consider this thought. If planetary systems all over the galaxy are busy shaping their own asteroid belts with unseen worlds, and maybe seeding them with the ingredients for life, what other cosmic structures are out there, waiting to reveal their planetary secrets? And how might they shape the destiny of whatever life emerges there, or even our own future expansion?
Makes you wonder what else is hidden in the dust.
It really does. Thank you for joining us on the deep dive. We hope this exploration leaves you with a renewed sense of wonder and maybe a deeper understanding of this incredible universe we're part of.